When considering derating factors for multiple conductors in a raceway or cable, it's crucial to understand how neutrals are treated. The general rule is that a neutral conductor is counted as a current-carrying conductor if it carries significant current. In a purely balanced three-phase system, the neutral conductor ideally carries very little current, and is often not counted as a current-carrying conductor for derating purposes. However, real-world systems are rarely perfectly balanced. Firstly, let's define what constitutes a current-carrying conductor for derating purposes. According to electrical codes, a current-carrying conductor is one that carries current under normal operating conditions. This includes phase conductors that supply power to loads. Now consider a scenario where you have 6 conductors, each with its own neutral. In this case, each neutral conductor must be evaluated to determine if it qualifies as a current-carrying conductor. Secondly, the determination depends on the type of circuit. In a 3-wire circuit consisting of 2 phase conductors and a neutral, the neutral typically carries the unbalanced current between the 2 phases. This unbalanced current arises because the loads on each phase are not identical. The greater the difference in current between the 2 phases, the more current the neutral conductor will carry. In such cases, the neutral must be counted as a current-carrying conductor for derating purposes. Thirdly, in a 4-wire Y system, which consists of 3 phase conductors and a neutral, the neutral conductor carries the unbalanced current among the 3 phases. The magnitude of the current in the neutral depends on how balanced the loads are across the 3 phases. If the loads are perfectly balanced, the neutral current will be 0. However, in practice, perfectly balanced loads are rare, and the neutral conductor will typically carry some amount of current. If the neutral current is significant, it must be counted as a current-carrying conductor for derating purposes. It is worth noting that the National Electrical Code, or NEC, provides guidance on when to count a neutral conductor as a current-carrying conductor for derating purposes. The NEC specifies that a neutral conductor that carries only the unbalanced current from other conductors of the same circuit does not need to be counted as a current-carrying conductor. However, if the neutral conductor carries a significant amount of current, such as from nonlinear loads, it must be counted as a current-carrying conductor. Fourthly, nonlinear loads, such as those found in electronic devices, can produce harmonic currents that flow in the neutral conductor. These harmonic currents can cause the neutral conductor to overheat, even if the fundamental frequency current is relatively low. In such cases, the neutral conductor must be counted as a current-carrying conductor for derating purposes. When applying derating factors, you must consider the number of current-carrying conductors in the raceway or cable. The more current-carrying conductors there are, the greater the derating factor that must be applied. The derating factor is used to reduce the allowable ampacity of the conductors to prevent them from overheating. Fifthly, the NEC provides tables that specify the derating factors for different numbers of current-carrying conductors. For example, NEC Table 310.15 B3 provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable. These adjustment factors reduce the allowable ampacity of the conductors based on the number of current-carrying conductors. To illustrate, let's consider an example. Suppose you have a raceway that contains 6 conductors, each with its own neutral. Assume that each neutral carries a significant amount of current and must be counted as a current-carrying conductor. This means that you have a total of 12 current-carrying conductors in the raceway. According to NEC Table 310.15 B3 A, the derating factor for 10 to 20 current-carrying conductors is 0.50. This means that you must reduce the allowable ampacity of each conductor by 50%. Sixthly, the ampacity of a conductor is the maximum amount of current that it can carry without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and the ambient temperature. The NEC provides tables that specify the ampacity of different types of conductors. For example, NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to 600 volts, based on their size and insulation type. Suppose that the conductors in our example are number 12 American wire gauge copper conductors with THHN insulation. According to NEC Table 310.16, the allowable ampacity of number 12 American wire gauge THHN conductors is 30 amps at an ambient temperature of 30 degrees Celsius. However, because we have 12 current carrying conductors in the raceway, we must apply a derating factor of 0.50. This reduces the allowable ampacity of the conductors to 15 amps. Seventhly, after applying the derating factor, the adjusted ampacity of the conductors must be greater than or equal to the non-continuous load plus 125% of the continuous load. This requirement is intended to ensure that the conductors are adequately sized to carry the expected load current. A continuous load is a load that is expected to operate for 3 hours or more at a time. A non-continuous load is a load that is not expected to operate for 3 hours or more at a time. Eighthly, if the adjusted ampacity of the conductors is not sufficient to carry the expected load current, you must either increase the size of the conductors or reduce the number of current carrying conductors in the raceway. Increasing the size of the conductors will increase their ampacity, while reducing the number of current carrying conductors will reduce the derating factor. Another consideration when dealing with multiple neutrals is voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. Ninthly, the amount of voltage drop in a conductor depends on the length of the conductor, the current flowing through the conductor, and the conductor's resistance. The longer the conductor, the higher the current, and the higher the resistance, the greater the voltage drop. The NEC recommends that voltage drop should not exceed 3% for branch circuits or 5% for feeders. To minimize voltage drop, you can increase the size of the conductors or reduce the length of the conductors. Tenthly, when you have multiple neutrals in a system, it is important to ensure that each neutral conductor is properly sized to carry the expected neutral current. If the neutral conductors are undersized, they can overheat and cause a fire. The NEC provides guidelines for sizing neutral conductors. For example, NEC section 220.61 provides requirements for sizing neutral conductors in dwelling units. This section specifies that the neutral conductor must be sized to carry the maximum unbalanced load. In addition to the NEC requirements, it is also important to follow good engineering practices when designing electrical systems with multiple neutrals. This includes considering the potential for harmonic currents and taking steps to mitigate their effects. 11thly, one way to mitigate the effects of harmonic currents is to use harmonic filters. Harmonic filters are devices that are designed to reduce the amount of harmonic current flowing in the neutral conductor. Another way to mitigate the effects of harmonic currents is to use oversized neutral conductors. Oversized neutral conductors can handle the additional current caused by harmonics without overheating. When working with electrical systems, it is always important to follow all applicable codes and standards. This includes the NEC, as well as any local codes or regulations. Following these codes and standards will help to ensure that the electrical system is safe and reliable. Derating calculations are essential for ensuring the safe operation of electrical systems, particularly when multiple conductors, including neutrals, are present in the same raceway. Understanding how to properly account for neutral conductors in derating calculations is crucial for preventing overheating and ensuring compliance with electrical codes. The NEC provides specific guidelines and tables to assist in these calculations, and it is important to consult these resources when designing and installing electrical systems. By following these guidelines, you can ensure that your electrical systems are safe, reliable, and efficient. Remember to consider the type of loads connected to the system and the potential for unbalanced currents when determining whether to count a neutral conductor as a current carrying conductor for derating purposes. When in doubt, it is always best to err on the side of caution and count the neutral conductor as a current carrying conductor.